So, this look ahead carry generation part, this portion, so we can make it a design which is again an iterative design. Suppose I have got this 4 bit look ahead carry generator circuitry. So, that has got CI as input, and it generates of course, this AI and BI, those XI and YI, those bits are there. So, it is not shown here explicitly. So, this GI and PI, so they are coming here in terms of that XI and YI. So, that part is not shown here, and it generates this CI plus 1, CI plus 2, CI plus 3, and it generates this PI plus I to I plus 3 and GI to I plus 3. So, those portions. Now, if we have got that this carry look ahead generator 4 bit version. So, now you can use it for 16 bit carry look ahead circuitry. So, we have got this 4 such carry look ahead blocks connected, and these carry look ahead blocks. So, they are getting say this say this say G0, P0, G1, P1, G2, P2, etcetera, and it is generating two one generate signal and one propagate signal. So, this generate signal will be fed to this CLA generator circuit. So, this is actually this block is similar to this block. So, whatever be the number of inputs here, similar number of inputs are there in this CLA generator block also, and we are just using some sort of hierarchical structure. Okay. So, this is using the same CLA generator block, but it is this G inputs are coming from this the corresponding CLA generator block of the previous level of hierarchy, and it is generating G 0 to 15 and P 0 to 15. That is the, if you take a 16 bit block, then this will be the generate signal from the 15 bit block, and this will be the propagate signal from the 16 bit block, and this is the propagate signal from the 16 bit block. So, you can cascade another such block here. So, to get a 32 bit block. Okay. So, that way we can go ahead. So, we can we will look into an example. So, these are simple formulas that we have got this delay calculations and all, like this GI-PI. So, the formula is GI equal to XI-YI. So, that will incur one gate delay, and this PI computation is XI XOR YI. So, that is also one gate delay. Now, this GI to I plus 3 and PI to I plus 3, they follow this particular formula, and here if I am assuming two level realization of the circuit, then there is one set of AND gates that will be realizing this GI plus 2 into PI plus 3. Similarly, GI plus 1 into and PI plus 2 and PI plus 3. So, this way it will be realizing the AND terms, and after that there will be an OR term. So, there will be 2 gate delay in the generate the GI to I plus 3 and PI to I plus 3. So, for this C4, C8 and C12, so we will have 2 gate delays. For G0 to G015 and P015, that will also have 2 gate delays. Now, for this C I plus 1, I plus 2, I plus 3, for I equal to 4, 8 and 12, they will see 2 gate delays. So, because of this expression, so if you look into this expression, so you will see how many gate delays are necessary. So, this way it can total 8 gate levels in the carry look ahead adder versus 32 gate levels in the ripple carry adder. So, if I am having a 16 bit adder, then there will be 32 gate level in the ripple carry adder, because this individual stage it will have their sum and carry. So, that will be the carry calculation will have 2 stages. Okay. So, that way it will have total 32 stage, but this if you are using this carry look ahead mechanism, so that will have only 8 stage. That is why this carry look ahead adder, so they are going to be much faster than this ripple carry adder, and in many applications where we need fast addition subtraction, so we go for this carry look ahead adder instead of ripple carry. Of course, the penalty that we pay is the number of gates that are needed becomes very high. So, this is the thing that I was talking about. So, this is suppose I have got this 16 bit carry look ahead blocks. Okay. Now, from there, so I can have some 32 bit block, and from there I can have some 64 bit block. So, here it is a 64 bit block that is generated, that is shown here in terms of this cascading of this clock generator circuit. Okay. and these are different gate delays calculations that we have. So, it is similar to the previous calculation. So, in that in summary you can say that a look ahead adder. So, now total if there is a carry bit k bit carry look ahead, then the total look ahead adder delay is 4 into log of k. So, that gives the advantage, like k equal to say if I have got the adder size of say 32, then look ahead adder delay will be 12 stages, and this ripple carry adder will have 64 stages. So, that was for 256 bit addition. So, look ahead adder will have got a delay of 16 stages, and carry ripple carry will have 512 stages. So, that is pretty high. Next we will be looking into decimal adder. So, decimal adder means that I have got the binary coded decimal digits BCD, and then I want to add them. So, in here, I have got the digits important for 0 to 9 only. So, rest are not important. So, they are coded like this. So, 9 is coded as 1001, and the rest of that 4 bit combinations are not valid for the BCD addition. So, these are the forbidden codes 1010, 1011 and all. So, for decimal adder, so we have got the inputs A3, A2, A1, A0, B3, B2, B1, B0 and C in from the previous cascade state, and output was C out and Z3, Z2, Z1, Z0. And so, what we do for decimal adder is that we perform regular binary addition and then we do some corrective procedure. So, for example, here we have got this number 0 to 9. For this part it is same. Okay. So, actually this is slightly shifted. So, this is for 0 to 9, if the decimal sum is equal to 0 to 9, then it is same. However, if the decimal sum is 10, 1010, so it will be represented in the BCD form. So, they will be represented as a carry bit being 1 and this Z3, Z2, Z1, Z0 being 0. Similarly, for 11, if the decimal sum is 11, then the C out will be equal to 1 and this Z0 will be equal to 1 and the rest of them will remain as 0. 12 will be like that. So, basically this C out bit will be set to 1 whenever the sum becomes greater than 9 for the BCD addition. Okay. So, this way I can so C out is 0 for this part and for other parts, so it will be equal to 1. So, no correction is needed when the decimal sum is between 0 and 9, and we must apply a correction when the sum is between 0 and 19. So, at most you can add to 9 and 9. So, that is at most the value can be 18. So, the value is between 0 and 10 and 19. So, you have to do some correction. So, this so these are the rules for BCD addition. So, when the binary sum is greater than 1001, we obtain a non-valid BCD representation, and the addition of binary 6 to the binary sum, it will convert the number to the correct BCD form. So, whenever it becomes more than 1001, so you just add this 6 to the binary to whatever sum you have got, and that gives the corrective action. So, to distinguish between 1000, that is binary 1000 and 1001, so which will also have 1 in position Z8. So, we specify that either Z4 and Z2 must have a value 1. So, C is equal to K plus Z8 Z4 plus Z8 Z2. So, this is the BCD sum part. So, this is 0100. So, this will be added if this Z8 so that if Z8 K4. So, if you look into this expression, it is K plus Z8 Z4 plus Z8 Z2. So, if this is the situation, then only the carry is generated. So, what we are doing for with this 4 bit addition result. So, we are trying to add this 6, but that is conditional subject to the case that there was a carry or this Z8 Z4 was equal to 1 or Z8 Z2 was equal to 1. So, if you draw the corresponding truth table, then we will find that under these conditions, so we need to do the correction of adding 6 to the binary addition result to get the BCD addition. So, a decimal parallel adder that adds n decimal digits needs a n BCD adder stages, and the output carry from one stage must be connected to the input carry of the next higher stage. So, that is obvious. So, if you need more number of decimal digits to be added, so then this entire block has to be repeated one after the other to get the BCD addition for higher number of digits. Next we will look into the multiplier. Now, you see that if I have got 2 bits A and B as input, then the multiplication is like this, A and B is, it is 0 1 0 0 0 1. So, if you compare with the AND operation, you see that we are getting the same thing. So, this AND is some sort of 2 bit binary multiplication. So, this by 2 bit binary multiplication is same as the AND of the 2 bits. For 3 bit multiplication, so suppose, so we have to, we will generate this partial product terms. So, 101 101. So, this 101 multiplied by 1. So, that generates this partial term 101. Then this 101 multiplied by the second one, that generates this partial sum, and then multiplied by 0, that generates this partial sum, and then we add all these partial sum to get the result. So, we have the partial products, and this partial product summation for n digit base 2 numbers requires adding up the up to n digits in a column. So, that way we are going to add these digits. So, that if I am multiplying an n by one n bit number by an m bit number, then we have to it will generate an m plus n digit number. Okay. So, that is there for multiplication. So, Boolean equations for multiplication. So, it will be like this. So, if I am taking as a 2 bit multiplication for example, then this generates A0 B0 and A0 B1 as this partial sum, and then this A1 B0 and A1 B1 as another partial sum, then these partial sums are added, the P0 P1 P2 P3, that generates the product terms. Okay. So, this is the circuitry for that. So, this generates A0 B0, then this generates A0 B1, A1 B0 and A1 B1, and then this A0 B0 directly gives it is not added with anything. So, that directly comes at the the result output C0. Then this A0 B1 and A1 B0 are to be added. So, I can use a half adder here because there is no carry. So, I can just use a half adder to do that, and then from this some carry may be generated, and that carry has to be added with A1 B1. So, this A1 B1 and that carry comes, and that will generate the sum C2 and the carry C3. So, this way I can use this circuitry to get a 2 by 2 binary multiplier. Now, some special cases. So, in decimal an easy way to multiply by 10 is to shift all digits to the left and put a 0 to the right end. So, 128 multiplied by 10. So, we know the result is 128 and a 0. So, we shift the numbers digits by to the left and put a 0 at the right end. So, for the same thing we can do with the binary one. So, we can shift left is equivalent to multiplying by 2. So, the shifting left is multiplying by 2. So, for example, this 1 1 multiplied by 1 0 is in decimal system it is 3 into 2, which is equal to 6. So, if you convert it into binary notation, so it is 1 1 0. So, what has happened is that this 1 1, so it has been left shifted, and this least significant bit position we have put a 0. Okay. So, that gives the binary shifting this multiplication by 2, and if you shift it twice, shift left twice, then it is a multiplication by 4. So, for example, this 1 1, so if I left shift twice, then I will get 1 1 0 0, and this number is nothing but 12. So, this 3 into 4 is 12. So, this is basically left shifting by 2 bits. So, shifting to the right is equivalent to dividing by 2. So, if you are so for example, this 1 1 0, that is 6. So, if you are shifting it by right position, so you are shifting it right means this 0 will go. So, 1 1 will remain. So, that is 1 1 and the result is 3. So, this is nothing but 6 divided by 2 is 3. So, this multiplication and multiplication by 2. So, this is basically left shifting the number by one position. Multiplication by 2 power I is left shifting the number by I positions, and similarly division by 2 is right shifting the number by one position, and division by 2 to the power I is right shifting the number by I positions. So, this way we can have the special cases for multiplication and division by powers of 2. So, for 4 bit multiplication, so 4 by 3 binary multiplier. So, we have got one 4 bit input B0, B1, B2, B3, and we have got 3 bit input A0, A1, A2. So, what we can do? So, we can generate these partial sums in this fashion. Okay. So, then they can be passed through some adders. Okay. So, 2 4 bit adders will be necessary and we can pass them through the adder, and ultimately we can get this sum which is consisting of 7 bit. So, 8 C0 to C6 plus there will be another carry. So, 4 plus 3 7, the result may be 8 bit also. So, that way there will be another carry generated. Okay. So, this way we can have these partial sums generated and we can do the multiplication. Of course, this multiplication process that we have talked about is pretty slow, and in case of integrated circuit chips, particularly in VLSI domain. So, you can find many other efficient multiplication algorithms that have come up. So, this is the basic multiplication algorithm that we have discussed, and the idea is to see how can we do it using logic gates and all. Next, we will be looking into another very important arithmetic module, which is known as magnitude comparator. So, I have got two inputs. I need to tell whether the one of them is equal to the other, greater than the other, or less than the other. So, if I have got a 2 bit value, so it is like this. So, suppose AB is the first number and CD is the second number. So, what is happening is that this AB is, if AB is 0 0, then if CD is 0, then this less than is 0, equal is 1, and greater than is 0, that is these two numbers are equal. So, this EQ output is 1 and this less than and greater than, these two outputs are 0. Similarly, if AB is 0 0 and CD is 0 1, so this less than output is 1, equal output is 0, and this greater than output is 0. Then this is 1 0, again the same thing. So, since this AB is 0 0, so whatever be the CD apart from 0 0, this less than will be 1, others will be 0. So, this way I can draw a truth table for, I can make a truth table for writing the entire behavior of this block of this comparator block. So, for doing the minimization, so we will need 4 variable Carnot map for each of these 3 output functions. Okay. So, we have to draw 4 variable Carnot maps, and accordingly we can do the minimization, get the circuitry, and ultimately we can say it is less than, equal to, and greater than these 3 outputs. We can see, we can draw the corresponding logic circuit. So, this is the thing. So, K map for less than is A bar B bar D plus A bar C plus B bar C D, EQ is this one. Okay. So, this A bar B bar C bar D bar, okay, or A bar B C bar D, that is either A and B. Actually, the logic is that A and B both are 0, C and D should also be 0. A is 0, B is 1. So, C should be 0 and D should be 1. So, this way I can do it. So, this equality, so if you look into it more carefully, so you can find that this can also be written as A XNOR C and B XNOR D. Okay. So, that way it can be there. So, this is the equal. So, that way we can draw the corresponding truth table, and from there I can get the logic functions realized in terms of basic logic gates. Now, let us look into this equality comparator more carefully. Suppose I have got only 2 bits to be compared and I have to say whether the bits are equal or not. So, in terms of truth table, so if it is 0 0, then the output is 1, if it is 0 1, it is 0, 1 0 is 0, and 1 1 is also 1. For these two cases it is 1. Now, you see that this truth table corresponds to simple XNOR logic. So, it is a 2 input XNOR gate. So, this is what is happening here. So, Z equal to X XNOR Y. So, this XNOR gate is an equality comparator. So, if I need a 4 bit equality comparator, equality detector, then this may be the block diagram of that. So, I have got this A 4 bit input A3, A2, A1, A0, and similarly B3, B2, B1, B0. So, this is the B 4 bit B input, and it answers A equal to B. So, this output is 1 only when this A and B input, this A and B inputs are equal to each other. So, I can take a very simple circuit consisting of 4 XNOR gates. Okay. So, this A0 and B0 fed to the first XNOR, A1, B1 fed to the next XNOR, like that. And now, this C0, C1, C2, C3, so they are to be ANDed. So, this AND gate is not, so they are to be ANDed to get A equal to B. Okay. So, that can be a 4 bit equality comparator. But what about a magnitude comparison? Like, so not only equality, I also want less than and greater than output. So, the A is less than B or A is greater than B. So, equality is definitely fine. So, how can we get A greater than B? So, how many rows will the truth table have? So, if we try to answer this question, then since there are 8 inputs A 0 to since we have got 8 inputs A 0 to A 3 and B 0 to B 3, total number 8 inputs. So, if I am trying to draw a truth table, so there will be 256 entries. So, if I am trying to draw a Carnot map, then it is an 8 variable Carnot map that we have to minimize. So, that is a very clumsy way, that is a very so far in our course we have seen that we can draw K map up to 6 variables, not more than that. So, that makes it difficult. So, we have to do something else for getting the minimized form. So, if you see that if A equal to 1 0 0 1 and B equal to 0 1 1 1, then A is greater than B. Why? This is because this most significant bit A 3 is equal to 1 here and B 3 is 0 here. So, A is greater than B. Now, because A 3 greater than B, so A 3, so the condition is A 3 B 3 dash or A 3 B 3 bar is equal to 1. Now, one term in the logic equation for A greater than B is A 3 B 3 bar. Now, what about this one? Say if I have got A equal to 1 1 0 1 and B as 1 0 1 1. So, here also A is greater than B, because the first two bits A 3 and B 3 were same and A 2 was 1 and B 2 was 0. So, I can say that A 3 is equal to B 3 and A 2 greater than B 2, that is why I have got C 3 equal to 1. So, C 3 equal to 1 if A 2 B 2 dash equal to 1 and A 3 equal to B 3. So, we have got so C 3 was A 3 equal to B 3, okay, the C 3 was A 3 equal to B 3. So, the condition becomes C 3 and A 2 and B 2 bar B 2 dash. That way, if we just shift by one more position, so you will get the condition, one more condition there. So, that will be this is the thing, that A 3 equal to B 3, A 2 equal to B 2 and A 1 greater than B 1. So, we have got C 3 equal to 1, C 2 equal to 1 and A 1 B 1 dash equal to 1. So, you see that the A 3 greater than B terms becomes C 3 and C 2 and A 1 and B 1 bar. And naturally, I will have one more stage where it will be doing this B 0 also, like only the B 0 the A 0 and B 0 bits are differing. So, if so this is the situation, the A 0 B 0 dash is equal to 1, C 3 equal to 1, C 2 equal to 1 and C 1 equal to 1. So, I will get the last term as C 3 C 2 C 1 A 0 B 0 dash. So, the final expression becomes like this. So, A greater than B is A 3 B 3 dash plus C 3 A 2 B 2 dash plus C 3 C 2 A 1 B 1 dash plus C 3 C 2 C 1 A 0 B 0 dash, and this can be realized by this circuit. You see that we have got a very clean circuit here, and we do not take help of the Carnot map and all. So, sometimes that process makes it very difficult, and we have to use some other logic to come to the circuit. So, similarly, you can say A less than B, A less than B is given by this formula A 3 dash B 3. So, A 3 is 0 and B 3 is 1, or A 3 B 3 are same detected by this condition C 3 and A 2 bar A 2 is 0 and B 2 is 1, or C 3 C 2, that is A 3 B 3 are same, A 2 B 2 are same and A 1 is 0 and B 1 is 1, and this condition A 3 B 3 same, A 2 B 2 same, A 1 B 1 same and A 0 is 0 and B 0 is 1. So, that way I can write down the condition for A less than B. Next, we will be looking into another important topic which is known as code converter. So, many a times we want to convert numbers coded in some number system into some other number system. So, that is known as code converter. So, they are coded in different form. So, this is a code converter, it is a logic circuit that changes data represented in one type of binary code to another type of binary code. For example, BCD code to binary code, binary code to BCD code, BCD to 7 segment binary, BCD to 7 segment display code, then binary to BCD, BCD to XS3 code. So, like that binary to gray code, gray to binary code. So, there are different types of codes that are there, and many a times we need to interchange between these type of codes. Okay. So, how to do these code conversions, that we will see now. So, two digit decimal values ranging from 00 to 99 can be represented by BCD in BCD by two 4-bit code groups. So, that can be utilized for doing this conversion. So, first we will be looking into BCD to binary conversion. Okay. So, one method for BCD to binary conversion is by some adder circuit. So, value or weight of each bit in the BCD number is represented by a binary number, and all of the binary representations of the weights of the bits that are 1 in the BCD number, they will get added. Okay. So, this way we can have some adder circuitry, and using that adder we can convert the BCD number to binary number. So, it is like this. So, 46. So, 46 this is the 4 this is the notation, and 6 this is the thing. So, this is the decimal number and this is the BCD number. Now, this most significant bit, it has got a weight of 10 and the least significant bit has a weight of 1. So, the most significant 4-bit group represents 40 and the least significant 4-bit group represents 6. Okay. So, because this weight is 10 and this weight is 1. So, this is 4 into 10 plus 6. So, that we can do. So, we can say that this bit position. So, this is decimal weight is bit position 1 and bit position 0. So, 10 to the power 0 and 10 to the power 1. So, if the binary weight of that, so if you look into that number at weight 10, okay, and look into the corresponding, if you look into the corresponding binary number, binary weight. So, this is 2 power 0, 1, 2 and 3. So, the BCD number, the BCD bit weight is 2 power 3 into 10, this is 2 power 2 into 10, this is 2 power 1 into 10 and 2 power 0 into 10. Now, so for example, this 46. So, 46 it has got 0, 1, 0, 0. So, this 0 gives a contribution of 0, then this so this 4 this 4 is represented by the first 4 bits and this 6 is represented by the next 4 bits, and for the first 4 bits they have got a weight of 10. Now, these numbers, so now this 0 multiplied by 10, that gives me 0, 1 is so this is 2 power 2. So, that is 4 multiplied by 10, that gives me 40, then this is 2 multiplied by 0. So, 2 power 1 into that value is 0. So, that is giving me 0. So, that way, so this part gives me 10 and this part gives me 6. So, binary equivalent of each BCD digit is a binary number and it is represented as a BCD weight bit. So, this is BCD position A, B, C, D, E, F, G, H, as we have seen here. This this bit designation A, B, C, D, E, F, G, H. So, they have got this BCD weight values like this and corresponding binary representations like this. So, this way we can do this binary to BCD conversion, like the result from this addition of binary representation of the weights of all the ones in the BCD number. So, that will give me the corresponding binary number. So, this is so 0 4 is 0 1 0 0. So, that is represented if we take the corresponding weight and all. So, the value was 40. So, that is giving it. Similarly, this was these two, this bit is 1 and this bit is 1, and for this bit I know that the corresponding weight is 4. Okay. So, this 4 is added and for this bit I know the corresponding weight is 2. So, this 2 is added. So, this gives me this number. So, after doing this all these additions, so it gives me 46 in the binary number. So, similarly, suppose I have to convert this 26 into binary. So, again we do the same thing. So, this part is all of them, they will contribute to 10. And this is 2 power 0 1, this is 2 power 1 2, 2 power 2 4 and this is 8. So, this is 2. So, 2 into 10. So, that gives me 20. So, I write down the binary representation for 20. Then in this part, so this part is to this weight is 10 power 0. Okay, for this all the 4 bits the weight is 10 power 0. So, this is this bit is 1 2. So, 2 into 10 power 0, that is 1. So, that gives me 2. So, I write down that binary representation for 2. Similarly, here I write down the binary representation for 4 and I sum them up. So, this gives me the binary 26. So, in this way we can convert BCD numbers to equivalent binary numbers. Of course, we have got other avenues. So, we can have a truth table and write down the corresponding Boolean functions for doing this conversion as well.